Welcome, folks. We're grateful for you spending this time with us this morning. My name is Denzil Ribeiro. I'm a principal product manager at Microsoft, and I'm honored and privileged to present to you the work that the team has been doing alongside Adam Prout, who's a co-presenter. So Microsoft has not been new to Postgres. We've been deeply involved in the Postgres ecosystem for years, contributing not only to upstream code, but sponsoring community events, and even running an enterprise service like Azure Database for PostgreSQL. With Postgres 18, our committers played a key role in upstream contributions, including some huge architectural changes and significant improvements like async I/O. So besides the contributions to upstream code, we also go way beyond code. We help shape some of the ecosystem with extensions such as Citus, with VS Code extension for PostgreSQL, and also participate in a bunch of community events such as PGConf, PGConf Dev, and even run our own conference called POSET. So our customers are betting big on Postgres. From startups to Fortune 500s, our contributions are driven by real-world needs, real-world customer needs, and we enable these customers to run their mission-critical workloads on Postgres. So with this background that we are not new to Postgres, I'm thrilled to announce HorizonDB, our next-generation cloud-native database that is built on the rock-solid foundation of Postgres. HorizonDB is more than just PostgreSQL in the cloud. It combines the flexibility of open source along with the scalability and intelligence of the cloud, and enables you to run modern applications from transactional systems to AI-driven workloads. HorizonDB is built for business. Enterprises require scalability, they require high availability, and they require enterprise-grade security. And it has all this from day one. And it's engineered for app devs. App devs love the power of PostgreSQL. It's one of the most popular databases. But along with that, they also want deep integrations into the dev ecosystem, which we give you with Azure. We have native support for AI workloads with features such as advanced disk-and indexing, as well as pre-built AI models on HorizonDB. And then we have tooling with VS Code extension that helps it all as well. So why HorizonDB? HorizonDB starts with Postgres for sure. So, Postgres is at the foundation of it. But it goes beyond that. There are some key tenets which we build the service with. Availability is one of them. Resilience and availability are paramount for mission-critical workloads. With single-digit or low single-digit failover times, with zone-resilient storage by default, and resiliency at every layer of the stack, HorizonDB is ready for mission-critical workloads. Performance is the second tenet. We have cutting-edge performance. It's predictable low-latency reads and writes. We optimize compute by offloading some of the tasks which are intensive, such as checkpoint to the storage layer. And then we have no impact of any of the sync replication implications when you have HA on Postgres. Then we have scalability. You can start small for startups with just a handful of cores, scale up to 192V cores, or scale out your reads. So scalability is another tenet which we build the service with. Oh, sorry, I forgot to click even my slides. From a security perspective, we offer enterprise-grade security with Entra-ID authentication. You can secure your network with private link. You have encryption. You have auditing. And last but not the least, it's app devs ready. So we offer a rich set of integrations with the Azure Dev ecosystem. We have integration with Fabric, where we can send changes to Fabric OneLake to enable real-time analytic scenarios. We have AI-assisted experiences via Copilot in our VS Code extensions. It also integrates well with the rest of the dev stack in Azure ecosystem. So with that, HorizonDB delivers cutting-edge performance. It's up to 3x faster than self-hosted Postgres on VMs for OLTP and vector searches. It starts out with a separation of storage and compute. You have a single copy of zone-resilient storage across the Horizon cluster. Each cluster offers a read and a read-write endpoint. And all the compute replicas are stateless. They scale up to 192V cores. You have a choice of adding up to 15 read replicas. And your applications can talk to this read-only endpoint and load balance this workload across these replicas. Then the database can grow as needed. Storage auto grows to up to 128 terabytes. There is near zero downtime with low single-digit failovers. And last but not the least, our commit latency is typically sub-millisecond with zone-resilient storage. So let's look at the stack bottom up. Explore that diagram a little bit more. At the bottom, we have a durable layer, which is Azure Blob Storage. This is your durability layer. And all storage layers, I'm not going to repeat this, but all storage layers are zone resilient by default. All your data changes come to this wall storage fleet. The wall storage fleet has resiliency and multiple data copies in it. It archives log to the durable storage, which is Azure Blob Storage. And it contains the tail of the log. In addition to this, we have the data storage fleet, which holds all your Postgres relations data, so all your table data. And this data is sharded across the fleet. And there are multiple copies and resiliency built in as well. All your data changes, your DML, inserts, update, deletes, first land in the log service or wall service. So this has a database as a log architecture that we don't actually flush data pages. All changes come as wall records or wall pages, right? And all of them actually land on the wall storage fleet, and then your transaction commit is done. This is then asynchronously played on the data pages to catch them up. And this data layer is shared, of course, across all your computes across the cluster, right? And there's optimized compute usage because we don't do full page writes in Postgres. We don't do checkpoints. Some of the wall archiving is all offloaded to the storage layer. So your compute is also optimized from that perspective. You get a better bang for your buck. And then you can provision a set of read replicas. All of these read replicas are stateless. They are also failover targets. They interact with the same storage layer. And then a read-only balanced endpoint actually will, you can direct your app to a read-only balanced endpoint, which then scales that workload through these replicas. All reads are shared storage. And then last but not the least, we have an SSD cache on all the computes to even increase that latency to microseconds of pages that are cached, so you don't have to go to remote storage. Last but not the least, if there is a page in memory, there is no direct connection between primary and replicas. If there is a page in memory that has to be caught up, log is set from the wall service to actually catch that page up. So let's look at the first peek from a provisioning perspective. We have a HorizonDB cluster. The cluster is a first-level ARM resource. That's what you'll see kind of in Portal. And so, all you need, the provisioning experience is super simple. You provide a cluster name, and then you configure it. Each core comes with 8 gigs of RAM, so all you have to do is configure the number of cores, and you choose the number of replicas. This is in addition to primary, you have 2 replicas in this case. And then you can choose the availability zone of the primary so that you can co-locate it with your app for good latency. You have Entra ID and Postgres authentication. From a network perspective, you can have firewall rules as well as private endpoints. And last but not the least, you just create it. So the provisioning experience is super simple. There you have your cluster. Of course, I fast-forwarded through this. We don't want to wait through a minute of provisioning. But you have your Horizon cluster with your endpoints created for you. Next, we're going to look at how compute read scales are actually done. So here on the left, I have a primary plus a read replica. And each of these clusters have a primary endpoint and a reader endpoint. On the left, I have just 1 read replica. On the right, I have 3 read replicas. And we'll see how reads scale through this. I have a pgbench workload, which is a read-only workload. And then I'm going to point to these 2 HorizonDB clusters. On the left, I have 32 clients because it's one replica. On the right, I have 96 clients because it is 3 read replicas. And you'll see the workload linear as you scale. You have around 90,000 TPS on the left and around 265,000 on the right. And really pretty linear scale from that perspective. Latency is low, and workload scales. In both cases, we are connecting to the read-only load-balanced endpoint. And now I'm going to call on Adam to go a little deeper into under the hood of how Horizon was architected. Thanks, Adam.
Thanks, Denzil. So my goal for the next 15 or 20 minutes is to give you enough of an intuition for how HorizonDB is built that you can see why we're getting these performance differences or these reliability differences. You don't need to know this stuff to use the system. It's more to give you that intuition. And if you take away only one thing about HorizonDB, it's that we're trying to take the greatness of Postgres. As Denzil said, we're big committers into open source Postgres and the community around Postgres. But Postgres was designed independently of the cloud, independently of Azure. And we're trying to then take that Postgres and kind of the puzzle piece that doesn't fit perfectly with the capabilities of Azure and just make it fit perfectly. We change Azure, change Postgres, and make this thing fit together perfectly. So if you only take away one thing, that's our the main thing we did with HorizonDB. Now, before we jump into some of these details, one thing I wanted to discuss is this is the first time, or almost the first time, we built a system completely in Rust in the Azure databases team. So most of our databases are C or C++. Of course, Postgres is C. And you might be asking yourself, hey, why do I care which language you use for your system? Well, Rust, if you're unaware of it, it's a system language. It can give you the performance of C and C++. But the language and the compiler gives you memory safety and some concurrency primitives that make it much easier to avoid bugs in your code. If it compiles, there's a certain class of bugs that just aren't there. So as someone who spent 2 decades building databases in C++, if you got like 1 million lines of code of C++, hundreds of developers changing it, there's just no way to avoid some buffer overflow slipping into your code. Some memory safety issues in your code. And Microsoft has the data to back this up. Like, obviously, we've been building stuff in C++ for many decades. We know that these are the classes of bugs that cause security vulnerabilities. So with HorizonDB, given we're starting from scratch, we said we're going to do it fully Rust from day one. So all the storage components I'm going to talk about in a few seconds are all in Rust. The extensions to hook the storage components to Postgres are also Rust. Some of the things we just built on our own, like the vector search components for doing approximate nearest neighbor search, that's all Rust. So we're really hoping that in the end we get a much more reliable, much more secure system. Because it was a little harder to build it in Rust. Like we wanted to kind of put that out there before we jump into the details. And there'll be a few parts. Well, I'll tell you, hey, Rust, and we had to do something different here, but. Just as the mindset we had going into this thing, let's build a reliable system. Let's not performance at all costs. Okay, so let's talk about that wall storage component that Denzil mentioned earlier. So, at least for the most of my talk, when I talk about Postgres, I'm talking about Postgres with HA configured, and there's lots of ways to do high availability with Postgres. But on the left side here, let's call this our canonical Postgres high available setup. So you have a primary, you have a hot standby, and in Postgres, when you want to commit on your primary, there's 4 steps that are going to happen on the slide there, and they happen in serial order. They don't happen in parallel. So Postgres is going to harden the data to its local disk on the primary. It's going to send the wall to the secondary. Secondary is going to harden it to its local disk, and then act back, and then your transaction is committed. So that's 4 serial steps. That's 4 things that if something breaks in any of those steps, you're going to have jitter or slowdown in your commits. And often in the cloud, in fact, step 1 and 3 are typically managed disks. So it's not even a local NVMe. It's like a network attached disk, say an Azure kind of premium SSD disk. So it could potentially be 4 network hops to commit. So with HorizonDB, we did something a little differently. We said, hey, we're just going to use specialized wall storage. All it does is store log. We'll talk where the data is stored later. And the reason we did this is because it has a very specialized pattern of reads and writes. And so one of the easiest things we can optimize here is we can commit in one round trip, one majority quorum round trip across 3 zones. It's always there under the covers. Again, you guys don't need to necessarily see this, but we're just kind of showing you how it works. So we're majority quorum across 3 zones, and your Postgres read replica in zone 3 in the diagram is just reading as fast as it can from that storage. But the primary and secondary in HorizonDB don't need to talk to each other. If your secondary gets slow for some reason, someone accidentally ran a really expensive query, your primary is committing away. There's just fewer points of failure, right? We don't have 4 steps. We have 1 majority quorum. So this gives us both performance and simplicity, right? There's fewer things to break. So let's dig into this in one more level of detail. So this is going to be, again, the purpose-built wall storage node. So we zoom into one of those wall storage nodes, what's inside of it. So, but first, let's motivate why it makes sense to do this. Like the transaction logs, right? Postgres just appending to them, right? There's just a stream, an LSN stream that's going up forever. We don't have to support random writes. So we can build a simpler system. We can build a faster system if we only need to support appends. The reads are typically only from the tail, right? If your read replicas are trying to catch up, they're not going to read from yesterday's data unless you have an emergency, a point-in-time restore. You want to go back to yesterday because something terrible happened, an accidental table drop. But we can do that from cheaper storage because it's going to be rare, right? Hopefully rare. So we can design a system around these principles that's much simpler than like a full managed disk. So how it looks is we have, and these are all the Rust components. And this is where Rust will play some role in the design, actually, of the system. So we took Postgres, and we have an extension there that uses IO_uring, which is just a new way of doing async IO in Linux. So like Linux had async IO for a long time, but like it was a lot of limitations, rarely used. IO_uring is much more performant, easier to use. We are taking advantage of it heavily here. So that quorum layer uses IO_uring to kind of synchronize out that majority quorum. When the wall writer gets one of these writes, it's also using IO_uring to write to the disk. But because we're just doing these appends, we don't need a complex storage system there. So there's no file system on these wall writer nodes. There's no Linux block device. We're just skipping these layers because we don't need them. It's just things that can add performance problems. It's more components we need to manage. They can have bugs. So like we just skip through them. We talk directly to the NVMe controller because it's a simpler storage system. We're like removing the sources of bugs from the product. And then of course it can move the data out to, archive it out to the blob storage as it ages. So back to the Rust part for a second here. So I said we're using IO_uring, but the nice part about this design is Rust is very famous for doing async await style programming. For concurrency. You can use threads in Rust, but typically you don't. But you can plug in your own runtime to control how the system runs threads. So that's what we've done here. And we're actually open sourcing it into the Rust community. It's called Kimo Geo. And it uses IO_uring under the covers. And the reason this is very nice is like when you look at our code, you just see like read and write system calls. They look like system calls. But like under the covers, Rust is running those on the async runtime, and it's using IO_uring. So we can build that IO_uring component once, use it in both places. We'll probably use it in other services in Microsoft, and you don't have to directly program it. So it's like, again, it's giving us that extra reliability. And we're going to open source this because this is something anyone can use. You can plug it into Rust if you want to have your IO done by IO_uring. It also does thread per core because, again, we're just doing a lot of I/O here. We don't want our units of work to jump around threads. It'll add more jitter. So it gives some nice capabilities to Rust. So we're going to open source that and work with the community to improve it. Before I show a couple benchmarks of this thing, I just wanted to complete the story. So we've been mostly talking about this piece right here when you want to commit writes. Right? We said that wall storage fleet only stores your log, your transaction log. We didn't say where the pages are stored necessarily. So asynchronously with your commits, we're sending the wall through a filtering service whose only job, it's a separate service. Again, we think it's more reliable that separate services specializing on particular things. It just reads the wall, runs the sharding functions, and figures out which data storage nodes care about this wall record, so they can redo the wall onto the pages. So Postgres doesn't have to. So this is your classic log as database design. There's lots of different ways of doing it. We think this is the best way with specialized storage, wall storage, a filtering component in between, and your data storage, which is also specialized, but it's mostly just doing redo. It's a cache, your data storage. The actual durable storage is zone redundant blob storage. As Denzil mentioned, all these components are zone redundant. It goes without saying. We're not going to keep repeating it. The reason this design is nice is because your read replicas, you can have a bunch of them, and they can all read from the same storage. They don't have separate storage each that you have to keep in sync. So let's actually see this in action. And this is not a scientific benchmark. Let me say that before people attack me. This is on the left, 𝗦𝗃𝗀𝗀𝗏. So this is that 4-step to commit diagram running. One community Postgres with one primary, one secondary on the left. On the right is HorizonDB. It's the same Postgres versions, the same regions, the same hardware, and we're just going to run pgbench because everyone knows what pgbench is in the Postgres community. It's an OLTP benchmark. And it's already warmed up and everything, so we're just going to let it run. And you can see HorizonDB is around twice as fast throughput-wise, and it's also about half the latency. That's all driven by these faster wall writes we're talking about. This is a very chatty benchmark with lots of these small little commits. So the faster you can make those commits, the faster this benchmark goes. And just to kind of drive that home, let's create a ridiculous benchmark where we just have a loop committing one write. Like you would never do this in the real world, but just to drive the point home that if you have lots of little chatty writes, whoops. Okay, here we go. We're back to the chatty writes. So here we have our loop. Now we're going to run it, and this is the same Postgres as we were showing with pgbench. So this is on the left, this is 𝗦𝗃𝗀𝗀𝗏, one primary, one secondary Postgres. On the right, this is HorizonDB. And here it's going to be about 3 times as fast. Because again, we're really just focusing on that faster write performance of the commits, which is exactly what HorizonDB is much better at. So again, non-scientific benchmark. It's just we're trying to show you what the system can do in different scenarios. Okay, let's switch away from kind of these performance things to talk about how the system does HA. Why do we get faster failovers and better reliability? So again, this is our classic Postgres HA setup. If your primary dies, there's going to be a failure detection that runs. It's going to notice it's gone. There's going to be a leader election. We're going to have a new secondary that's promoted to primary. Everything is kind of good here. Now the issue is, well, your old primary is gone. Maybe you have another secondary if you wanted to pay that cost, but you're definitely down some level of availability. You want to get that old primary back as a secondary as quickly as possible. And with standard Postgres, because your old primary has its own copy of the log, it may have diverged from the new primary. Because remember, we had that 4 steps to commit. The first step was the primary writes to its local disk. And boom, failover right there. That data never made it to your secondary. If your old primary comes back, it's got to fix that. So Postgres has some tools to fix this. It's not like it's an unknown problem, but it takes time to do it. And even worse, if your old primary is completely gone, it's never going to come back, you have to either get a disk snapshot or a full backup and try to get that thing back in the cluster. So there's a lot of steps there to restore availability with your standard Postgres HA setup. With HorizonDB, the first part's going to look kind of similar, right? Postgres primary goes down. We have failure detection. It's a little bit different here because we have one log storage that's shared between the two of them. So we have to have an RPC that runs called a ring fencing command that says, hey, that Postgres is now the primary. It can do writes. Because by default, the wall storage fleet is going to reject writes from anyone else. Now, here's the part where it gets a little different. When the old primary comes back online, because it's stateless, right? It doesn't have its own copy of the log. It can just start reading again from the wall storage fleet. It doesn't have to do any rewind. It doesn't have to do anything. And if your old primary is lost and you need to provision a new one from scratch, it's almost the same steps. It doesn't have to do anything. It It talks to the storage fleet to get an LSN to start reading at in the log, and then it starts reading, right? There's no extra redo from a checkpoint that you would have in standard Postgres. So let's see, again, unscientific benchmark, our same two clusters that we've been dealing with, 𝗦𝗀𝗀𝗏 on the left with community Postgres, and HorizonDB on the right. And we're going to have pgbench running here in the background, and we're going to run some inserts, I think. There we go. And the inserts are just there so we can see when the failovers start failing queries. So we're going to trigger some failovers, and we're just going to see how long it takes for the failover to happen on both systems. So because the compute is stateless on HorizonDB, we can be much more aggressive about the failovers. They're kind of harmless. It's easy to add the nodes back. So I think it's going to be around 4 seconds before the failover happens, and your insert pings that we're running here start succeeding again. With 𝗦𝗀𝗀𝗏, it's going to take a fair bit longer to trigger that failover. There it goes. So I think it's going to take around 20 seconds to do the failover, get the workload succeeding again. But on top of that, the problem is if we wanted to immediately have a failover again, we're just going to kind of demonstrate. 𝗦𝗀𝗀𝗏's going to say, no, I can't do it, because it takes me some time to repair Postgres. Where in HorizonDB, there we go. See, the 𝗦𝗀𝗀𝗏's going, no, what are you trying to do? It takes me some time to repair things. With HorizonDB, we don't have that issue, right? So we have faster failovers, and you can fail back more quickly, pretty much instantaneously, right? The primaries and secondaries in HorizonDB don't even talk to each other. Okay, let's switch gears from writes to reads just quickly. I wanted to because there's some confusion around this, like, oh, if you have separated storage, your reads must be slow, but they're not. Like, it's still Postgres on your compute, right? We still have shared buffers there, which is nanoseconds to read from memory. Where it gets a little different is there's an SSD cache on fast NVMe disks. This comes by default. You don't have to configure it. And so there you have tens of microseconds if you need to read pages beyond your memory. And if you need to read pages beyond your local disk, that's when you go out to the storage fleet. And this is sub-millisecond reads at like P99. Probably P70, it's closer to half a millisecond. But you only need to go there if it's overflowing your working set on the local disk. And so this gives you the ultimate flexibility. You can decide, hey, my workload is not fitting on my compute, so let's grow the compute. You'll get more memory, more local disk. Or my workload is fitting. I just want to grow the amount of data I'm storing. Okay, fine. The storage fleet will grow underneath of you. You can keep your compute the same size. You don't need to resize anything because it's being kept up to date with the wall, like we mentioned earlier. And kind of quickly, we wanted to discuss how the data is stored. So the wall's in the wall storage fleet. And we're trying to keep as close to classic Postgres as possible. So if you look at like a Postgres data directory, you'll see these 1 gigabyte segment files, a lot of them. That's just how Postgres stores its data. And in HorizonDB, Postgres still believes it's storing its data that way. There's no reason to change it. We're trying to have minimal changes to Postgres. But what we did is split that data up, and we store it in the page server fleet, whose main job is running redo, keeping those pages up to date as the wall flows to it. And we store 1 copy in zone redundant blob storage. And why this is handy is because we can do multiple copies for HA across the page server fleet, because we want that redo to be keeping up. We don't want to fall behind in our page server fleet. But even better is what happens when we want to grow and shrink, right? Because we don't, like if you look at classic sharding designs, like typically the data gets shuffled around when you want to add another shard. But here, because we have the copy of the data, 1 copy in blob storage, if we want to add another shard, we can just pull that data from the blob store. There's no like shuffling anywhere, right? The data in the blob store doesn't change, right? We're just taking those files and moving them around to different page server nodes, and we can read them in bulk from the blob store. So this can happen in like tens of seconds. So it makes the system nice and elastic. Like as you insert more things into Postgres, We can look at the balance on our storage fleet and add and shrink it as necessary. It's a quick, painless operation. There's not like a big data reshuffling going on. So this is basically how we make the system elastic, so you can store up to 100 terabytes of data in it if you want to. If you delete some data, the system will just shrink. You don't have to worry about it. Okay, so that's kind of a whirlwind tour of some of the under-the-covers stuff for HorizonDB. We'll talk in more detail maybe about some of the other things, but let us know what you're interested in hearing about. And my kind of closing comment is there's a big team at Microsoft working on this product. It's a big investment for us. So now is the time to give us feedback. If there's something about Postgres that's bothering you, now is the time. If there's something about any SQL service that's bothering you, or any data service, hey, I wish I had this thing, now is the time. Because we have our list of what we think is important, but now is the time to influence us. So come and talk to Denzil, myself. There's lots of people from the Postgres team here. We have a big booth. But back to Denzil to finish up.
Thank you, Adam. Now we'll talk about a few things that investments we're making with respects to AI on HorizonDB. And there will be an AI session separately, which I'll point you to. So DiskKNN is a state-of-the-art vector indexing algorithm from Microsoft Research. It's designed specifically for large data sets, scaling vector search or similarity search to large data sets. Compared to the traditional HNSW or IVF flat, DiskKNN outperforms it. And you can see the speeds in some of our testing. And it's both in latency and accuracy. But we have seen in our testing up to 10x faster speeds, up to 4x lower costs, and up to 32x less memory that is used. Right? So DiskKNN, one of the key innovations in DiskKNN is product quantization, where you take these large dimensional vectors and you compress them down into compact representations. And this enables, reduces the amount of memory, so it allows more vectors to actually fit within memory. And as a result, you do less I/O, right? So you get performance improvements as a result. So less I/O means less latency, higher throughput. And unlike other quantization efforts, these efficiencies allow you to have ANN or nearest neighbor searches with minimal accuracy degradation. And then we are introducing something new called advanced filtering. And this aims to address a common issue with vector search, which is combining vector search along with other database predicates or filters. In real life scenarios, you don't do vector search or similarity search in isolation. You also have filters that you apply or predicates that you apply. For example, you're filtering on a product catalog or a price or a date range or any of the above, right? In traditional indexing, if you look at HNSW, any of these filtering is a multi-step or multi-stage iterative, and post-filtering applied to get accurate results. And this results in slower, less efficient searches. With advanced filtering, we have filter-aware search, where the filter and the search is done in a single step. And as a result, this is 3x faster than DiskKNN without advanced filtering. And DiskKNN by itself is faster than HNSW. So, from a performance perspective, there's huge value in this. In addition, we are introducing AI model management. Now, you can interact even today. You can interact with AI models, but you've got to provision AI Foundry resources. You've got to put your embedding models there and then use the Azure AI extension to actually call into them. With AI model management, we simplify this. It's a single-click deployment which will configure Postgres components required, configure the Azure AI Foundry, deploy pre-built models, and then give you an integrated billing, monitoring experience. So your time to value reduces greatly with this, right? So how this will look like is you enable model management on the HorizonDB server, And as a result, you get some pre-configured models. An example is embedding. You have text embedding 3 small, or chat completion, you have GPT-5. For semantic re-ranking, you have Cohere re-rank, right? But along with this, it also provisions the the Azure resources required for it, giving you integrated billing, giving you monitoring, cost management, and then installs the Azure AI extension within the Postgres database and exposes these models with aliases so the application can directly use operators on top of it, right? And what are these operators? These operators are things like create embeddings. Create embeddings allows you to work on a data set from within SQL. All these operators allow you to embed AI workflows within SQL, within your database. So you don't have to leave the language you know from a database perspective. You're working with all these models right within SQL, right? So create embeddings is a call which you can call into the embeddings model and generate an embedding for text or images that you already store in the database. Generate is one that provides structured text. So for example, you can pass a prompt saying, rewrite this text with a particular prompt. Is truth evaluation around a statement. Extract, you can give a phrase any text, and it extracts some entities based on labels that you actually provide. And then rank, of course, gives you ranking based on relevance. But these are operators which, via the Azure AI extension, along with the pre-built models embedded, give you a seamless experience within HorizonDB. So, for the AI demos and much more in-depth AI session, you should look at the BRK130. We have a blueprint for intelligent AI agents. Alongside with that, we have a few other sessions, including some AI labs, which are super popular. Feel free to check these out. And last but not the least, here's a preview link. At this point, HorizonDB is a gated preview. As Adam said, this is the time to actually try it out and give us feedback and affect our trajectory. We would love to hear back from you. I will be at the booth tomorrow. We have other folks at the booth tomorrow. Feel free to find Adam or me. Happy to answer any questions at this point of time.